So there was mention of this in a couple of talks today, the difference between data parallelism and task parallelism. And this is an oversimplification of these two categories, which aren't exclusive and don't cover the whole space, but they're useful to think about. Data parallelism often arises from the fact that physics happens in parallel and is local. That's sort of the fundamental idea for so many of our PDE-based simulations. And we've looked at this Laplace equation, for example, very typical example of data parallelism where same operations are carried out on different data. We have to communicate between the various patches in order to put together the global picture. Communication is necessary between these patches, and load balancing is sometimes needed, but it's not the main theme because we've tried to divide things up so that every process has about the same amount of work to do. Task parallelism is, the way I think of it, is different in the following way. The tasks are largely independent. They might be of widely varying sizes, might be quite different types of computations. There might be no communication at all between these tasks, or a little bit. And at least the old-fashioned way of doing this, we had a separate master task for scheduling. And in this case, load balancing is absolutely fundamental to how the parallelism works. So our definition of load balancing is, again, a very simple one, just the scheduling of tasks, where task is some code and some data, to processes so as to minimize the total idle times of the processes. So static load balancing, it's sort of what we do with data parallelism. All the tasks are known in advance, and we decide who's going to do each task, and they do it, and we don't need a coordination process. And at least the old-fashioned version of dynamic load balancing has a master process that assigns tasks to workers, and when a worker process becomes free, says, okay, I'm done, I'm free, the master finds another task for him to do and gives it to him. And this was, in some ways, is at the heart of the Charm++ system. This requires some communication, but only between the manager and the worker processes. Usually it's easy in this situation for tasks, the completion of one task to result in the creation of some new ones that weren't there before. But certainly there's no problem with the tasks being quite different from one another. So this has often been implemented. Maybe your first parallel program looked something like this. You have a manager and a bunch of workers. The manager has a queue of work. It's very easy to implement this kind of model in MPI where the manager communicates with the workers. And it solves some problems very easily. That's what makes it an attractive model. You automatically get dynamic load balancing. If one worker is slower or working on a bigger task, then the others can keep working on the pool of tasks. It's easy to manage the termination. It's easy for the manager to look at the results that a worker gives him and add some extra tasks to the work queue. Can use this to implement a workflow structure because the manager can see what's happening. It does provide scalability problems, which is the sort of motivation for the library I'm going to talk about. In particular, the manager can certainly become a communication bottleneck when instead of 5 workers, we have 1 million workers. Memory can be a bottleneck if there isn't room for all the tasks on the manager process, so we're going to have to distribute those as well. So it was this idea and a motivating physics application that I'll talk a little bit about near the end that spawned the idea for what we call the asynchronous dynamic load balancing library. And so the idea is not to have a master process at all, because workers don't need to know what the manager is doing. They only communicate with him in order to put a task in the pool. So let's make that the API, not sending and receiving, but putting tasks in the pool and taking them out. And maybe that's all we need. Maybe we just have 2 operations in our library. And as we'll see, we can get away with almost that. And we'll use a simple put and get interface for the application code, and then we'll hide all the MPI code somewhere. So the application just replaces sending a completed work and asking for that communication to the master just becomes putting work in the pool. If he's creating it, taking it out and working on it, maybe putting an answer back to the master. And this is going to give us an opportunity to do some fairly fancy stuff in the background to do the load balancing among the workers. So our picture has turned upside down like this. We just have workers, and the shared work queue is an abstraction that's implemented in some way. We don't have to say what that is as long as we can implement the API. So it doesn't really change the algorithms and the workers. This is not really a new idea. There was a programming system called Linda. It's quite old that works sort of like this. But the tricky bit is to get a scalable and portable distributed implementation of this work queue. And if we want to scale to 1 million workers, then we might need some sophistication in the implementation of this queue. We're going to use MPI, and we're going to use some of the more sophisticated aspects of MPI, but we're going to hide it from the application in this concept of the work queue. So the ADLB library, this is all of it, and you really only need to know the red things. So an ADLB put takes a work unit, which is defined just by an address and a length in bytes. That is, we're not going to pre-decide what work units look like. And the get is really in 2 parts. You can reserve work because you might not know how big a work unit you're going to get, and it gives you back a handle and the length and gives you a chance to allocate some memory, and then you get that reserved thing. And the rest of things are just really housekeeping. We'll talk a little bit.
Sorry, what's the target rank?
Optionally, you can specify on the put that you want a specific guy to be the only one allowed to get that. And the usefulness of that is that you can do message passing that way.
I was just making sure it wasn't mandatory.
No, it's not mandatory. Exactly. That would ruin everything if it was mandatory. But sometimes you'd sort of like to do some message passing, but although you could use MPI, you'd just as soon not do it that way. It lets you do load balancing in your message passing, actually. So there are some notes on the API, which you can find out more about if you want to download this and look at it. If some parameters are default, this becomes a very simple, high-level work-stealing API. We'll look at some examples of various complexity. If you use the fancy parameters like the target rank, we have priorities, there are types of work, there are ordered types, so forth, that let you actually implement some fairly sophisticated algorithms just in terms of this essentially 2-function API. And doing that, you can do fairly sophisticated things. For example, the Swift workflow management language uses ADLB as its execution engine. So there are a number of implementations, and we keep fiddling with it. The production one, that is the one you will get if you download what I'm going to tell you about later, works something like this. The ADLB servers, some number of processes are servers, and the application processes are their clients. They communicate by doing puts and gets with their server, and the servers communicate with each other to keep track of where the work units are, so that if somebody asks for work and that server doesn't have work of the right type, he knows where it is, and so he can get it and so forth. But the application processes don't see any of the complexity that's going on as the servers communicate to try to essentially implement this large shared data structure of work units. The implementation, that is the communication that's going on amongst the servers and in the library part of the clients, uses a number of MPI features. So you'll see that when you initialize ADLB, you're essentially carving off a set of servers. A communicator is returned that the application can use for its own MPI communication if it wants to. So using ADLB doesn't preclude the use of MPI. And you shouldn't just think of, well, it would be misleading to think that there are 5 servers, because in one of our big physics applications, there are 10,000 servers, but then there are 1 million clients. So this scales up beyond what I could draw a picture of. We use iProbe for the servers in order to be very responsive. We use MPI data types extensively for communicating among the servers. There's a status vector that is circulating around the ring of servers. Everyone uses non-blocking sends and receives. We use an MPI idiom that not very many people use. Although we're doing an iSend, we have a queue of outgoing messages that have been put there with an iSend. We don't wait on them. We just keep testing them until they're gone. You don't really have to wait on an MPI iSend. You can just keep testing it. And the client side in the servers uses the MPI synchronous send. So that waits until the receive is posted on the other side. That keeps there from being too many unexpected messages arriving in the server. So we keep things in the client until the server is ready. And we use the MPI synchronous send as exactly what that's for. And when there are requests from the servers, they respond with an MPI ready send. We talked about that the other day, how if there's a request, you can know that the receive is posted. That means that the response, giving the response to the query, can be sent in an accelerated way with the MPI ready send. And since everything is MPI, this is very portable. You can run it on anything. So all codes start a little bit like this. You have to do an MPI init. You set some parameters. The key thing is ADLB init, which you specify a number of servers that you're going to use, and you get back an application communicator that does not include the servers, and you get back a flag that says whether you're a server or not. If you're the server, you call the server routine, and now you're a server. Otherwise, you're application code, and so you just proceed. So let's look at a wide range of applications here. So as a sort of a tutorial example, I'll show you a bad algorithm for solving Sudoku puzzles, but it's really easy to write. A real live example of a physics application that takes advantage of the simplicity of the interface. We have a batch scheduler for clusters that shows how compact the code can be. And then finally, we'll look at a serious application that actually stimulated the development of the library. So does everybody know how to do Sudoku puzzles? Sure you do. The idea is you read this puzzle in the newspaper, and your job is to fill in all the squares so that the numbers 1 through 9 occur in each row, in each column, and in each of the boxes. There are a lot of different strategies. I'm going to demonstrate a strategy that's probably not a good way for you to do it, but it's really easy for ADLB to do it. So we'll say the work unit is one of these partially completed boards, and so we'll do it this way. First thing we'll do is read the initial board out of the newspaper and put it in the work pool. So work pool has one work unit in it. And then everybody executes the code that starts here. So all the processes do this. They try to get a board to work on. Of course, right at the beginning, only one of them succeeds. The others wait. And if you get one, if there's none there, then we're all done. We'll see how that happens. We'll look at this. This stands for optional optimization here. We'll look at that and then a little bit later. So in the board that you've got, you find the first blank square. If there isn't a blank square, of course, you're already done. So you tell ADLB you're done, which has a special effect. Otherwise, you just look at the possible values and set the blank square to that value. That adds one new value. And you put the new board in the pool. And then you go through this loop again. You go get another board, and gradually the pool fills up the more branches there are. But gradually there won't be any valid values except, and then that will not put a new board in the pool. And so eventually the pool will swell up and then it will go down. I think I have, this explains what happens. So you put the original one in the pool and somebody gets it. So there's the first blank square. The only possible values are 4, 6, and 8. So you make these 3 boards and you put them on the pool. So everybody just keeps turning through the same thing. So you've got a very, very simple code here. And eventually, since every time a board goes in the pool, it's got 1 fewer blanks than it did before, pretty soon you solve the puzzle. And you can optimize this staying within the ADLB framework. For example, if you want to do something fancy because you already know how to do Sudoku, you can fill in more squares before you start the branching part of it. But even so, there's a lot of work units. Just this problem, when I did it on my laptop, I think it reported actually looking at about 300,000 work units before finishing in about 5 seconds. Just one example of an idea, you can use priorities. ADLB tries to, if you say a work unit has a higher priority than another, and it can give you either one or the other, it'll give you one with high priority if it can. It doesn't try very hard to do that, but it tries it a little bit. So if we just set the priority to the number of filled squares, that is, we'd rather work on a more completed board than a less completed board, we'll end up with roughly a depth first search, which is the way you'd like to do it if you're doing it by hand. And ADLB automatically figures out when there's no more work, and everyone can terminate. So that's one simple example. The interesting thing about this one, there was some physicists at Argonne heard me give this talk, and they said, well, we've just got a lot of separate simulations to run. We're looking for material. There are a lot of different, it's a parameter study. There's a big space of parameters, and we want to explore it and find out what combinations give us the best results. So these are completely separate simulations. And so they downloaded ADLB, and I never heard from them again. And so I thought, well, that was a bust. And about 2 years later, I ran into one of them in the cafeteria and said, how come you never worked on that? He said, oh yeah, it worked great from the beginning. We've been using it all the time. They never called me. It's true, usually when you get called, it's a bug in your program. And in this case, they didn't know anything about parallel programming, and they never learned any more about parallel programming. So it's an example of something that, for them anyway, was very productive. I saw that on a small cluster we had, we didn't have any sort of batch scheduling system, and we wanted one. This was just a small cluster of Unix systems. It's turned out to be, we wrote this in about an hour. It's a very simple thing. The input is a stream of Unix command lines. That's the simplest possible way to specify a job, just strings. The master process reads them in, dumps them in the pool. The clients get them out and just call system on that command line. So at least for systems that have Unix, this is really pretty easy. And then it's very easy to add priority considerations to this using ADLB priorities. So now, it isn't all just fun and games. The actual motivating application for this was a program called GFMC. It's been one of the high-end nuclear physics programs for a long time at Argonne. Steve Piper of the physics division at Argonne was a friend of mine, and he's always been one of our aggressive users on the big systems at Argonne. And so this was back in the time of BlueGeneL. He had it's a Monte Carlo program, so the work units don't really communicate with one another. It's a big search for a Green's function. So it's an integration, it's a Monte Carlo integration problem in a way. And so he had a sort of a non-trivial, but it still was a manager-worker algorithm with different wrinkles in it. So, but he hit a scalability wall at about 2,000 processors because his master process couldn't handle it. And when he had to, what he would do is shut everything down for a bit and shift work queues around and then start back up again. But at 2,000, he kept having to do that too often. So he needed some sort of continuous load balancing instead of periodic load balancing. So as the algorithm threatened to get more complex to try to do bigger calculations, we tried to do something different. And it was a huge code, so he didn't really want to change the overall idea. And so that's when we invented ADLB. We got rid of all his master-slave type load balancing and did it the ADLB way. And this worked out quite well. It's turned out to be a multi-step process. We originally were just thinking about balancing the processing load to do one of these integrations. It turned out that we need to do memory balancing, that is, one server can start to get too many work units and it has to shift some of its work to one of the other servers. Now we have to update our big index of where all the work units are and so forth. And then ultimately we had to balance the communication as well. So it was a multiple balancing process. But while we were doing this, and we were doing some fairly fancy stuff to do this, we never had to touch the application code at all. And now it runs on 100,000 processes. We don't have to do it that particular way. Here's something that we're working on now. The idea is to have only one server, but not have it be in charge of the data. It only keeps the index of where the data is. So this lets us eliminate multiple views of the data structure and have the data structure that says this work unit of this type is on this process, and then have the client processes communicate with each other to get and put the work units. So they have to, when they put something to the master, it has to know where things are, and when they ask for something, the master will tell them, well, go get it from this guy, and then they will do that. And we use the passive target remote memory operations. This is still in the stage of using the MPI2 versions. And this hasn't scaled as well as the other scheme so far because we ended up with network congestion at the master who has to deal with lots of small messages. So if you'd like to play with this tonight or any other time, you can get it from here. My colleague Ralph Butler keeps it at MTSU. If you go there, you'll see the documentation, including the details of the API, download button. It'll get you a tar file. It'll have all the source code. It'll have the Sudoku solver and the batcher and the traveling salesman problem, which is just another type of simple example. I think this is a path through all of the cities in the United States with a population of 50,000 or more, or something like that. And to run your application, configure, make, run with MPI exec, and you're done. Have any problems? If you do this tonight, you can get help by raising your hand. Otherwise, send mail to us. So our conclusions are that there is a lot of benefit in the programming models area to limiting the generality of your approach. Almost everything that we've talked about in the last couple of days have been general purpose programming models that you can do anything with. Well, ADLB is not a good way to solve the Laplace equation. It's good for other stuff. And you can get scalability without necessarily having complexity in the programming model itself. The idea of ADLB is to make the programming model for the application unbelievably trivial, and you get the scalability by making the implementation of that unbelievably complicated. But that's the computer scientist's job, not the application guy's job. And finally, ADLB might be handy for you. And that's all.